Whether we are designing an HPC system or executing a specific task on an operational HPC system, there are a few basic laws of computing that we need to be familiar with that will govern how we approach this. Understanding and respecting these laws is paramount to maximizing your performance. Arguably, the most well-known of the laws will be Moore's law. A simple explanation of this law is that the number of transistors on the same surface area will double every 18 to 24 months. This effectively means we should expect to double our computation capacity every 2 years, all things being equal. Now the second law, which ties in with the first law, is the memory wall. What this says is that as CPU performance doubles every 2 years or so, memory performance has practically leveled out, only increasing at a factor of 1.1 times every 2 years. And if it's not clear, the implications of this is that CPUs are left waiting for memory. So this affects performance and shows why CPUs alone are not the be-all and end-all of a performant HPC system. The next law is Amdahl's law. And this law is only really a law that you'll worry about or be exposed to when you're working in a parallel computing environment. This law says that you will only experience a performance improvement relative to how much of your task you can convert to be parallel. In other words, just because you have enough compute nodes to perform something in parallel doesn't actually mean it will improve performance. Think of it like you're ordering coffee. If you have one customer ordering coffee, it doesn't matter whether you have 1, 2, 3, or even 50 coffee machines and 50 staff to run them. And for those interested, here is a function of Amdahl's law which will help you to calculate the overall speed up based on the fraction of what you're improving. Next is Ladmer's law, but this is kind of a bit of a joke title because it's actually Amdahl spelled backwards. But what it emphasizes is actually still quite important. Whereas Amdahl says make the common case fast, Ladmer's law says do not mess up the uncommon case too badly in the process. So let's take a look at a practical example of Ladmer's law in action. Let's say, for argument's sake, that you can find 90% of your problem can be doubled in speed through some parallel optimizations. That would be the common case. 90% is a significantly common case. It's a large majority. But the remaining 10%, the uncommon case, will be suffering from a factor of 10 times slower performance overall. From Amdahl's law, we know that the speed up will work out to 1 over the 10% divided by the speed improvement, which in this case is 10 times slower, which means it's 1/10 of the original speed, plus 90% over 2 times speed. This simplifies to 1 over 1 plus 0.45, which works out to 0.7. That means that this actually results in a slowdown. In fact, if we were to assume that we could get an infinite speed improvement for the 90%, which is the common case, but we still suffer a 10 times slowdown for the remaining 10%, the uncommon case, we'll end up with 1 over 1 plus 0, which is 1 over 1, which results in no effect on the actual performance. And that, in a nutshell, is the spirit of Ladmer's law. It's basically that even if you have a huge worsening on a small part of the problem set, it will have a massive impact overall. Now, going back to the parallelize versus parallelize mantra, I want to introduce you to my own law of HPC called Cole's law. Just like we all love coleslaw and we want to add it onto everything, it's a common misconception that simply adding more will be better. Why do we say that? Well, we touched on this briefly with the memory wall, but there are many other factors that play into Cole's law. Data transfer can be a massive bottleneck as you pass data to hundreds or thousands of compute nodes. Just remember Cole's law, and it will remind you of the common misconceptions behind parallelization. More cores do not guarantee more speed. In other words, more is not always good. And why? Because sometimes we can parallelize things and not parallelize things, and that is Cole's law. And the type of the data being passed, whether it's big files, small files, large chunks, small chunks, the type of information being shared, what form of I/O it's going to follow, etc. All of those things and many more can all play a role in the underperformance when adding more components or resources into the mix. We'll dig into this much more in a later chapter, but just remember for now, Cole's law says Moore's law isn't always good.